for his speech today. And I'd like to add, we had a great time with Dr. Sabine and Ove last night, and some of the other speakers sitting in the guest house, and some of the students were reveling in the fact that they were listening to researchers debate the next statement for the IPCC next year. Will it be coming out this year? Next year. We're thrilled to have Dr. Sabine here, and it's little wonder that Chris was drawn to study the ocean. As he mentioned yesterday, he grew up near the water, and as his family lived on a boat for 1.5 years in the Caribbean, sailing around the Bahamas and the Gulf of Mexico, and then still lived on that boat when they moved back to Charleston, South Carolina. Chris's interests were broad as an oceanography student, but he settled on becoming a chemical oceanographer, and his work led him to examining the carbon cycle. Now, the scientific community had known for a long time that carbon dioxide levels were rising in the atmosphere, and simple chemical equilibrium would dictate that dissolved carbon dioxide levels in the ocean should rise too. But as we heard yesterday, the ocean is very complicated, and it's so vast. The ocean contains about 50 times more carbon than the atmosphere. And we've increased carbon dioxide in the atmosphere by about 40%. Now, how could that have much impact on the ocean? Scientists had another dilemma. It was clear several decades ago that carbon dioxide levels in the atmosphere did not match emissions due to fossil fuel burning. There was less in the atmosphere than we expected. Where did all the carbon go? And we really didn't have data to show that. Was it terrestrial plants, or was it the ocean, or a combination of both? We're very pleased to welcome Dr. Christopher Sabine, a pioneer in constructing ocean carbon budgets, to tell us this fascinating and urgent story of how he and fellow scientists are unraveling the mysteries of the ocean and the carbon cycle. Dr. Sabine.
Well, thank you very much. First of all, I'd like to start off by thanking President Oley and the faculty for this wonderful degree. I'm honored and pleased to receive it. It's quite a humbling thing in recognition of all the past scholars that have received this degree, and I hope that I'm worthy of it. I think one thing that I probably share with those scholars is a real passion for the work that I do. And I guess if there's one thing that I'd like to pass on to the younger generations and students that are here, it would be to find something that you're passionate about. If it's not the oceans, perhaps it's something else. It could be art, it could be history. Whatever it is, find something that you're passionate about and pursue that dream, pursue that direction, and you can achieve amazing things. The topic I'll be talking about today, I am extremely passionate about. That is understanding the ocean's role in the global carbon cycle and how the burning of fossil fuels and human activities are impacting our oceans and our marine ecosystems. So I'll talk a little bit about that today. If there's one take-home message that I'd like to leave with you, I'll give that right at the beginning. It's a similar message that we got yesterday from some of the talks. Basically, that is that regardless of who you are, where you live, all humans on the earth are having a profound impact on the global ocean and the creatures that live there. And we need to recognize that and acknowledge that and take actions to try and preserve what we've got in our marine ecosystems. I'll go through 3 components today in my discussion. First, I'd like to describe the rising atmospheric carbon dioxide concentrations, what's causing that, where the CO2 is going. I'll discuss the impact of that rising CO2 on the oceans and its marine ecosystems. And because I've been told that some of my talks at times can be a bit depressing, I've added a new section on perhaps suggesting some things that we can do to help that. So we'll see how that goes. Hopefully this is a figure that most of you are at least a little bit familiar with, the fact that CO2 is rising in the atmosphere. The blue dots on the right of this figure show the measurements that we've made over the last several decades. That's shown in the expanded version in the middle of the plot here. But in the big plot, I'm showing CO2 for the last 1,000 years. Concentration is shown on the vertical axis on the left in parts per million. It's very simple. That's just if you were to take 1 million molecules of air, how many of those would be carbon dioxide? And it would be, in the pre-industrial, that would have been around 280 out of those 1 million molecules would be carbon dioxide. And you can see that for 1,000 years before the Industrial Revolution, which was in about 1800, the CO2 concentrations were extremely constant. These are measurements made from ice cores where they take a slice of ice and ancient atmosphere is trapped in the bubbles, and they can measure the CO2 in those bubbles. These records actually go back almost 1 million years now, and we've seen that even going back as far as 1 million years, the CO2 has never been higher than about 290 parts per million throughout that whole record. And in fact, we believe that you can go back as far as perhaps 50 million years and not see CO2 higher than it is today. And yet, since the beginning of the Industrial Revolution, we've been burning fossil fuels and releasing CO2 into the atmosphere, and which has resulted in an exponential growth in atmospheric CO2. And we know that very well from our direct measurements. What's causing that? It's the burning of fossil fuels and other human activities. This is our estimate for 2010. Fossil fuel burning was about 9.1 petagrams of carbon per year. Now, one thing I find when I'm talking to people is that basically no one has any idea what a petagram is. We heard the talk last night about the iron in femtomoles, which is 10 to the minus 15. Well, it turns out a petagram is 10 to the 15, so a 1 with 15 zeros after it. As I talk to people about that, okay, that sounds like a lot of zeros, but so okay, well, let's try something different. How about it's 1 billion metric tons? Okay, well, maybe that's starting to sound like a lot, but still hard to grasp, kind of like the deficit, you know? It's such a large number. So I've come up with an illustration that will hopefully try and illustrate how much CO2 we're actually putting into the atmosphere. So I ask you to consider a coal train, a boxcar with coal, which is about 80% carbon. That railroad hopper car holds about 100 US tons of coal. That's 80% carbon. And that railroad car is about 60 feet long if you include the couplings. So the question I pose to you is, how long do you think a train would have to be to hold just 1 petagram of carbon? It's funny, when I go and talk to students about this, you know, they'll guess maybe 100 miles, or some will even guess as long as the country. It turns out, when you go through the math, that train would be 156,500 miles long. 156,000 miles long. To put that in perspective, the circumference of the Earth at the equator is about 24,900 miles. So that means that a railroad train holding just 1 petagram of carbon would stretch around the Earth more than 6 times. We're releasing 9.1 petagrams of carbon per year into the atmosphere from burning fossil fuels. You add to that the deforestation. We're cutting down trees at a rate of about 28,000 square miles each year. That's almost the size of the country of Panama that we're cutting down and burning every year. That's adding another 0.9 petagrams of carbon per year, giving us a total in 2010 of about 10 petagrams of carbon per year. That means that coal train holding the amount of CO2, the amount of carbon that we've released in 2010 would wrap all the way around the Earth 63 times. People say, the Earth is huge. We can't be affecting it. But if you think about the numbers, it's a clear gas. We don't really see it. But if you think about the numbers, if you think about just how much CO2 we release from almost everything we do, it really is quite staggering. So where does that CO2 go? We burn it in our power plants, we burn it in our cars, it comes out into the atmosphere. Now this is an oceans conference. You're saying, why am I talking about the atmosphere so much? Well, it turns out that only about half of the CO2 that we release is staying in the atmosphere. Where's the rest going? As Jeff mentioned in the introduction, when I first started working on the global carbon cycle, we really didn't know where it was all going. But we think that we've closed that budget now. And our estimates are that approximately half of that remaining carbon is going into the terrestrial biosphere. We all know that plants breathe in carbon dioxide and release oxygen, while animals breathe in oxygen and release carbon dioxide. Turns out that many plants, particularly trees, grow faster in higher CO2 environments. And that fertilization, together with the reforestation of areas that were cut down many years ago, is helping to absorb carbon dioxide that's released into the atmosphere now. But the other half of that is going into the oceans. And as an oceanographer, I'll be focusing the rest of my talk on that piece that's going into the oceans. Because that's what really got me into this, is trying to understand, why are the oceans taking up CO2? Where is it going? And what impact will that have on our global oceans and marine ecosystems? Now, why are the oceans important? It turns out, actually, that the oceans are one of the most important components when you look at CO2 on time scales that we're considering, that is, kind of years to centuries. When you consider on that time scale, there are really 4 pools of carbon that we need to consider. There's the atmosphere, of course, which is collecting the CO2 that we're releasing. There's the land plants that I mentioned, and below them are the soils. The soils are releasing CO2 into the atmosphere as well. But there's also the oceans, and there's a great deal of natural carbon in these 4 pools. But of all that carbon, 90% is found in the oceans. So ultimately, it's the oceans that control, in the natural system, where all the carbon is going and the state of carbon in the other pools. This is just a simple cartoon illustrating the basic carbon cycle in the pre-industrial. So this is prior to the human intervention. What we find is that the oceans typically were a source of CO2 to the atmosphere. They're releasing, on a global scale, the oceans are releasing CO2 into the atmosphere. That carbon was then absorbed by the trees. As the leaves fell off those trees and the carbon was remineralized, it went down into the rivers, was transported down into the oceans, where it was then released. So we have this giant cycle of carbon in the Earth's system, with CO2 coming out of the oceans into the trees and then back to the oceans. The atmosphere, as you saw in those ice core records, was extremely constant in its concentration. If you look at the numbers that I'm showing here, the loss of CO2 from the atmosphere, the exchange, is on the order of 70 petagrams of carbon per year. The only way that the atmosphere could remain that constant is if this whole system is more or less in balance. So we believe very strongly that there was a strong balance, particularly since the last ice age, over the last 11,000 years or so, between the atmosphere, the oceans, and the terrestrial biosphere. And think about what's happened over the last 11,000 years. That's the period over which our society developed. we have developed our society based on a constancy of climate. We know that we plant corn in the Midwest in June, or whatever it is. Sorry, I'm from Seattle. We don't plant corn. So what we've done now is we're modifying that system. So over the last 200 years, we've started tapping into a reserve of carbon that was tied up in the rock record, that had we not tapped into it, would have stayed there for tens or hundreds of millions of years. This is carbon that was sequestered. It was removed from the system and was not part of those four pools that I discussed that normally exchange carbon. But because of humans drilling and mining, we're pulling that carbon out of the earth and putting it back into the atmosphere. And this is the average for the last decade. You see this number is a bit smaller. Fossil fuel burning, the average for the last decade was 7.7. I told you in 2010 it was 9 petagrams of carbon, so we're continuing to expand our emissions. The red arrows show the enhanced exchanges of carbon because of human activities. So while we still have this natural carbon cycle, I hear people say, but carbon, we couldn't have life on Earth without CO2. That's very true. And carbon is a natural component of our life cycle. The plants couldn't live without it, we couldn't live without it. But on top of this natural cycle, which was in balance for so many years, we've now added this carbon that was sequestered in the rocks. And that has basically reversed the role of the oceans in this global carbon cycle. Where the oceans used to be a source of CO2 to the atmosphere, now they're a sink for CO2. They're actually taking up more CO2 out of the atmosphere than they're absorbing. And that has consequences for how the oceans operate, for the chemistry of the oceans. We know this because we can measure it. We've gone out and we've made measurements that actually show this rise in CO2. The red dots on this figure are the atmospheric measurements that were started by Dave Keeling back in the 1950s on the island of Hawaii. And he very carefully made the most precise measurements and showed the steady increase of atmospheric CO2 in the relatively clean airs around Hawaii. So in the late 1980s, early 90s, we started doing the same sort of measurements in the ocean, saying if we're seeing all this rise in CO2 in the atmosphere, do we see the same thing happening in the surface ocean? And in fact, we do. The blue dots show the measurements from the Hawaii Ocean Time Series station. I started these measurements when I was in graduate school in Hawaii, and they've continued on since then. And you can see they're much more variable, but in general, the surface ocean is increasing at about the same rate as the atmosphere. And this is basically what we see in most areas around the global ocean. There are a few regional differences, but on a global average, we believe that the surface ocean is increasing at about the same rate as the atmosphere. Together with that rise in surface ocean carbon dioxide, we also see a drop in the pH of the oceans. And here's where I have to apologize. I'm a chemist, and I think it's required that whenever a chemist speaks, he must show some equations. So I don't want you to check out. I know a lot of you are groaning, particularly up in the balconies. Oh, God, here we go. I promise only 2 slides, and they're very simple. But CO2, carbon dioxide, is what we call an acid gas. The CO2 molecules react with the water molecules in the ocean to form carbonic acid. That's why we talk about ocean acidification. As an acid, that molecule releases some of its hydrogen ions, and that's what we're measuring when we're measuring the pH of the ocean, is the increase in those hydrogen ions. Now, those hydrogen ions don't just sit there. They're important because they react with other molecules, and I'm just going to talk about one, and that's the carbonate ion. We find that more than 99% of those hydrogen ions that are released react with the carbonate ion to form another compound called bicarbonate. Now, why do we care about the carbonate ion? That's because a lot of organisms in the oceans produce calcium carbonate shells. Here's my last equation. What we find is that organisms like, think about your corals, your oysters, your mussels. Think about the white sand beaches of Hawaii. That's all formed from calcium carbonate. And this is where the organisms take a dissolved calcium ion, they grab a dissolved carbonate ion, they put that together, and that makes a solid. They use that to form their shells or their skeletons. And that's calcium carbonate. Now we want to look at that and see how that might be changing as we add CO2 to the oceans. A way to do that that sort of simplifies the way we can look at that is using this index that we call the saturation state. And it's just a relative indicator of how easy or difficult it is for those organisms to produce their shells. Okay? It's set up so that any value less than 1 means that if you were to put that shell into the water, it will begin to dissolve just on its own. And the higher that index, the larger that number, the easier it is for those organisms to produce their shells. So let me just show you an example with talking about coral reefs. We're going to hear a talk later this afternoon by Ove, who's going to tell you all about the coral reefs and all the different pressures they're facing. I'm going to focus just on the carbon impacts on this. So we can take the measurements we've done and the models we've run. This is actually a result from a model run by Ken Caldera, and we've verified this model, confirmed it against some of our measurements. But this is a measure of the index level for that saturation state throughout the global oceans. The scale is shown on the bottom. Again, the higher the number, the easier it is for those organisms to produce their shells. The lower the number, the more difficult. On top of this color scheme that I've shown here are these magenta dots. The magenta dots are the locations of all the known warm water corals in the world. And this is a figure showing the pre-industrial concentration, so prior to about 1800. We can see that basically all of the known coral reefs in the world were growing in these blue waters. These are the waters with very high saturation states, very easy for them to grow. And the histogram on the bottom shows, the histogram here shows where the distribution of all those corals are. So you'll see that all these corals basically are growing in these blue waters. So what we want to do is look at how that might change as we step through time. So this is the pre-industrial. Here we were at the turn of the century. So CO2 had increased from 280 to 380 parts per million. You see that the corals haven't moved, but the waters around those corals have changed. There's a lot less blue in this picture. And you see from the histogram that now about half of the corals are in this kind of moderate zone. So the blue is optimal. The oranges and yellows are moderate. They can still grow, but not very fast. By the time you get into the reds, the corals basically are stopping, are no longer growing. They're just existing. And then when you get below 1 into those pinks and whites, that's where the corals will just naturally dissolve and dissolve right out from under. So what happens as we step forward? Here's where we're going to be within the next 20 years or so. Almost no blue left. We see that almost all of the corals are in this moderate zone, so they're still growing, but likely more stressed and difficult for them to continue to sustain themselves. What about the end of the century? Estimates for the end of the century range from, say, 550 up to possibly as high as 750 parts per million. These are very modest estimates of where we might be by the end of this century. Not that far from now. Some of you up in the bleachers will still be around then. You see that basically there's no blue left anywhere. That the corals will not be dead, but in our estimates, many of them will not be viable to continue to grow and sustain themselves. And when you add that together with what you're going to hear from Ove this afternoon of all the other pressures that are facing the corals with the rising temperatures, with all the other pressures, scientists are extremely concerned about where we might be in the future with our coral reefs. I'll leave that to Ove to give you that good news. That's just one example of the kinds of things that we're looking at. We really started this work from a chemical standpoint of trying to say, all right, we know that carbonate ion is going away, and that's going to make it more difficult for organisms that produce shells to grow. But in fact, as this research has grown, this is really a new field, but it's been exploding. There's been an exponential increase in the number of studies made on ocean acidification and potential impacts over the last 5 years or so. We're seeing all kinds of different things. Not all of them are negative. We see, for example, that photosynthesis generally increases in higher CO2 levels, particularly with nitrogen-fixing cyanobacteria. They seem to grow much faster in the higher CO2 environments. But it seems the predominance of the impacts that we see generally are negative impacts on marine organisms. Now, these are the direct impacts, and there's actually some other surprises too. We heard the wonderful mercury talk last night. It turns out that a lot of the heavy metals that we worry about in the oceans are very pH dependent. So as you change the pH of the oceans, you change the state of some of those metals. So iron, for example, is a micronutrient that's needed by some plants to help them grow. It turns out that as you lower the pH, you make iron less available for some of those organisms. Copper, which is a poison to many organisms, becomes more toxic under low pH environments. So there are impacts that we didn't even think of when we first started doing this work that we still need to try and understand. Things like sound absorption. It turns out that a lot of the compounds, dissolved compounds in the ocean that absorb sound currently are very pH dependent. As pH goes down, those compounds change their form, and we're anticipating that the oceans will become more noisy. There'll be less absorption of sound. How might that impact our marine mammals and organisms that use marine echolocation? And how will that be impacted as we increase our anthropogenic noise from shipping and other sources? So there are all kinds of new areas of study that we're trying to work on. Now, yesterday, I saw there were lots of really cool movies and videos and pictures. As a chemist, it's really hard to do that, so I had to put this in last night. This is my token video of a cool creature that I put in just for you guys. So this is what we call a pteropod. He's a cute little planktonic mollusk. He's a little snail that spends his whole life swimming around the ocean like this. They've modified the foot so that they have these wings, and they basically fly around. And you can see that he's got a shell around his body. And that shell, it turns out, is very susceptible to changes in ocean acidification. And they're one of the more vulnerable species that we're looking at. Now, you may say, all right, do I really care about a little marine snail that's swimming around in the ocean? But what we're starting to study now and trying to understand is to move beyond just the direct impacts of the CO2 and the ocean acidification on marine organisms, and to think about how that may affect things further up the food chain. And this is just, again, one example with the pink salmon. There was a study done there have been studies done for a number of years in the Gulf of Alaska, up in the area where I'm from, looking at why do we have more or fewer salmon recruitment, salmon growing up to be adults that we can catch from one year to the next. And there have been millions of dollars spent on trying to understand the impact of changing temperatures on these salmon. Well, some studies were done a few years ago looking at the diet of these juvenile pink salmon, again, just as one example, and they found that almost half their diet was made up of these pteropods, these organisms that we think are going to be put in jeopardy with ocean acidification and may no longer be around. And what they found was that while a 10% increase in the water temperature leads to a 3% drop in the mature body weight of a salmon, this is what they've been studying for years, that a 10% decrease in the pteropod production actually leads to a 20% drop in the mature salmon body weight. This is a new area of study, a new impact that we didn't even consider a few years ago, that we're now trying to understand. What might these cascading effects be? You know, we may not care about pteropods. I don't know about here in Minnesota, but in Seattle, we really care about salmon. And so this has become a big issue for us. So as we start to study these different impacts, we need to try and better understand what's going on. And I will say that this is still a very new area of concern, where there's a lot of new research coming out. We're finding out new things all the time. Again, there are pluses and minuses. There are winners and there are losers. But we feel, those of us scientists that are studying this feel, that there's enough evidence that suggests that this could be a problem, that we need to take action now. So where do we go from here? As mentioned, I've been a part of the Intergovernmental Panel on Climate Change. This is an organization that pulls together thousands of climate scientists every year to do an assessment of the current state of the climate and our understanding of the science backing up that state of the science. And I think it's really fascinating. One of the things that the IPCC does is to look into the future and think about how things might change in the future. And they develop these things called scenarios. And so early on in the IPCC process, back in 1990, there was a group that put together these scenarios and said, all right, how do we think CO2 emissions might change in the future? They said, for the next 10 years, we don't see things change really very much. So we'll just assume that things will continue as they have for the next 10 years until, let's say, the turn of the century. But by the year 2000, surely there'll be all kinds of new technologies out there and improvements that we can make. And they came up with a range of scenarios that involve future emissions, future technologies that would allow us to become more efficient and have alternative fuels so that we're less reliant on fossil fuels. And they projected, and tied up in here is the growth of the human population, our energy needs. So they put together these different scenarios for how CO2 emissions might change in the future. And I think it's really fascinating that there were a lot of arguments at the time that this came out. You see that most of these estimates are on the order of 1% to 2% growth in the CO2 emissions. There was one that received a lot of criticism, this A1F1 scenario, that had a 2.4% increase in our growth of CO2 emissions. It's this red line up here. One of the higher ones that people were saying, there's no way that we will go over a 2% emissions globally. So these are all global numbers. So I find it really fascinating now, 20 years later, to go back and say, well, so let's see. These were their estimates back in 1990. How are we doing? So these are our actual emissions, global emissions of CO2 over the last, between 2000 and 2008. And what you see is, or between 1990 and 2008, and what you see is that between 2000 and 2008, our CO2 growth rate has been about 3.4% per year. Now, I've stopped this plot in 2008. Anyone know what happened late in 2008, 2009? It's when we had our global recession. You put on the 2009 number, we actually saw a drop in the global CO2 emissions. We can make a difference. Now, I'm not saying the recession is good, but the point is people say, oh, well, we can't change that. You know, it is what it is. But in fact, we can. We don't need a recession to do it. We just need to make a decision to make a difference. Now, that was 2009, and there were a number of scientists in the IPCC that looked at that and said, okay, we've had this kind of step decrease in our CO2 emissions. What's going to happen in the future? And they were projecting that, all right, we'll just continue on that same path, but with this kind of offset from that 1 year once the economy gets going again. So that was 2009. If we add in our 2010 number, we had the largest single-year growth in CO2 emissions over this whole period. And we're basically right back up on that red line. And it looks like 2011 is going to be very similar to that. So, what does that mean? Getting back to the oceans, I guess another point that I would like to make is that it's not just the magnitude, the amount of carbon that we're adding to the atmosphere. It's the rate that we're adding it that makes a difference. This is a plot from Ove that he'll be speaking this afternoon. But he was pointing out that if you look back over the last 500,000 years or so, the rate of change of atmospheric CO2 was less than 1 part per million per century. Over the last 200 years, we've increased CO2 from 280 to today it's about 392 parts per million. Over the last 100 years, the rate of increase of carbon dioxide in the atmosphere is about 50 times higher than anything we've seen in the geological past. And our projections for the future over the next 100 years range from 150 to perhaps as high as 400 times the rate of change that we've seen in the past. So yes, CO2 has been higher in the past. CO2 was higher during the time of the dinosaurs, during the Jurassic period. But think about, what was the environment like during the time of the dinosaurs? Was it the same environment we have today? Even on top of that, it's this rate of change that's important. So I guess my second point that I'd like to make, in addition to the fact that all of us are contributing to this effort, is that even if we can't completely stop burning fossil fuels immediately, which I realize is an extremely difficult problem, if we can at least slow it down and give our marine ecosystems and our Earth an opportunity to adapt to the changes that it's experiencing, we at least are giving the Earth a chance. Let me tell you one more story with the premise of if we can slow things down, we can at least begin to think about and consider possible adaptations and alternative approaches for the future. Again, I'm from Seattle, from the Pacific Northwest. Oysters are a big industry where I come from. These are the oysters that we've got in our area in Washington State. Commercial oyster hatcheries are about a $100 million a year industry, about 3,000 jobs. Yet for the last 7 years, there's been essentially zero recruitment of new baby oysters into the wild, natural estuaries in the Pacific Northwest. This, of course, had a number of the people alarmed. It's actually a scenario that's happening all around. The Chesapeake Bay oyster industry has already collapsed. We're seeing this all around the country and all around the world. Where are the oysters going? One thing the oyster hatcheries figured out pretty early is that it seems to be associated with upwelling. This is a term that you've heard a couple times yesterday. I thought I'd just quickly explain what that is. On the west coast of the United States, in the summer, we typically get winds that come from the north and blow right along the coast. What that does is that pushes water offshore, that surface water, it moves it off the coast, and that water then gets replaced from below. So it's called upwelling. It's where the water is physically dragged up to the surface from below to replace the water that's moving offshore. And that water from below typically has very high natural CO2, low pH, and low oxygen. And that has real consequences for the marine ecosystems that live there. So one of the things we did back in 2007, when we realized that there really were very little data looking at the carbon system along the upwelling coast of the west side of North America, we put together a cruise and went out on a ship and made some measurements. And I'm going to show you just some example data from this line 5, right on the California-Oregon border, where we went out in June and we saw this strong upwelling. So you see offshore here, you have a typical temperature structure where it's warm in the surface and cold down deep. But as you move on to shore with these winds and the upwelling that's occurring, you see that cold water is being dragged up onto the continental shelf, which is shown here in the gray area. So that's what upwelling is. It brings that cold, deeper water from, 150, 200 meters up onto the shelf. This is the temperature structure, and here's that saturation index. So this is that ratio that I showed you where I said if the values get below 1, which are shown in the blue and purple colors here, that means that calcium carbonate shells, the shells of those oysters, clams, mussels, will just naturally begin to dissolve if they're exposed to these waters. We're seeing these waters being brought right up onto the shelf and all the way to the surface. And this is the pH. If we look at the pH, these are very corrosive, low pH waters that are being brought up onto the shelf. As we surveyed the whole shelf, we can see on the left, you see the surface aragonite saturation concentrations, again with the blue values indicating the areas where we see undersaturated or these corrosive waters all the way right up at the surface. But if you look down at the bottom, so right along the continental shelf, right along the bottom waters, basically we saw these corrosive waters everywhere along the west coast of the United States. This was not predicted a few years ago. The global models that we were running were saying that we wouldn't see these waters, corrosive waters at the surface for another 50 years. But in fact, that physical mechanism of the upwelling, bringing those deeper waters up into the shallows and up into our estuaries, is bringing those corrosive waters right up onto the shelf even today. And our estimates are that figuring out the man-made component of that in the pre-industrial, although there was upwelling in the 1800s, the CO2 concentrations were lower and those waters were not corrosive, not as corrosive as they are today, and certainly not below this critical level of 1. So what we did was we started working with the shellfish industry saying, okay, we see that this upwelling is bringing these corrosive waters up. Could that be what's causing some of the problems with the oysters? And what they found was from tank studies looking at the oyster larvae, what they found was the oysters spawn, so they release their eggs out into the wild and they drift around and for a while, and that's how the oysters spread out. At some point, those larvae start to form their shell, and that shell is what makes them heavy so that they settle out, and then if they happen to settle into an area where they can attach and grow, then they're happy as clams. What we found from some of the tank studies was under elevated CO2 conditions, they just can never generate that initial shell. And so they never settle out. So they just end up floating around until they die. And we think that's what's happening. So what we did was we put some sensors into these hatcheries. And this is work that we've done with our colleagues at the University of Washington and Oregon State University, and in partnership, close partnership with some of the shellfish hatcheries like Taylor Shellfish and others. But what they saw was when you have winds from the south, so remember I said it was the north winds that caused the upwelling. When you have winds from the south, you don't have the upwelling. We see lower salinity because that means that there's more local water from the estuaries, which have rivers flowing into them. So that's just an indicator. That's when they were getting a good survival of the larvae. and we see these very high saturation states. So when you have winds from the south, when you don't have the upwelling, the oysters are very happy. When you do have the winds from the north, so here we're seeing the winds from the north, these upwelling favorable winds, we see higher salinity. That's indicative of more water coming in, this deeper, colder, higher salinity water coming from offshore into the estuaries. That's when all the larvae are dying. So that showed us and showed the shellfish growers that in fact chemistry does matter. It's not just biology. Sorry. I'm not sensitive about that. Working with the shellfish industry, we were able to make some suggestions on how they might change some of their protocols. Another thing they did was they were flushing their tanks with water from the estuary once a day. They would come in the morning and flush their tanks first thing in the morning when they got to work. That's absolutely the worst time to do it. At night, you've got respiration. You've got all the animals and the plants breathing out carbon dioxide. The highest concentrations of CO2 we see in the water are first thing in the morning. If you're going to flush your tanks once a day, do it in the evening after you've had all day of sunlight for the plants to grow and absorb that CO2 where you have the lowest CO2 concentration. So making some of these simple changes in their protocols, by their estimates, the estimate of the shellfish industry in the Pacific Northwest, they're estimating that we save them about $35 million a year by just changing some of their procedures based on what we've learned about the chemistry of CO2 in these waters. Now the problem is this is a short-term fix. We can tell them, we can help them to correct some of the things that they're doing now, but ultimately this is a global problem. We're seeing the CO2 increase everywhere in the world, and sooner or later we're going to have these high CO2 values everywhere. So what can we do? There are a number of different approaches that we need to take. The first of which, and the main one that I'll just focus on today, is conserving our resources. Even without thinking about changing technologies, it is estimated that we can save as much as half of our CO2 emissions just by changing our practices and conserving our resources so that we don't burn as many fossil fuels. This is just for the US, our fossil fuel emissions between 1973 and 2010. You see that we've seen a dramatic increase in our emissions from transportation. Transportation actually accounts for about 28% of our total emissions on a national level in the United States. And think about the average car in the United States now, average automobile owned by an individual, gets about 17 miles per gallon. If we can improve the fuel efficiency of those cars by 10 miles per gallon, just one car, improve fuel efficiency by 10 miles per gallon, so from 17 to 27 miles per gallon, if you drive 10,000 miles a year, you can save 4,400 pounds of carbon dioxide that you're releasing into the atmosphere. We have cars now that can get 40, 50 miles per gallon. Another thing we can do is to think about our electricity use. These others, the residential, the commercial, and the industrial, represent most of those emissions are from generating electricity to run those businesses or to run our homes. 41% of the total emissions of CO2 in our country come from electric power generation. There are alternative ways of generating that power, and most power companies now offer green power opportunities. You know, is it worth paying a few extra cents per kilowatt to help save the planet? I think so, and I think Ove will talk a little bit more about the potential for moving from a fossil fuel-based economy to some alternative approaches. It's not just the United States. It's been noted that our emissions in the United States actually have been dropping a little bit. You can see that here. Actually, we've seen a dramatic drop over the last couple of years, again, associated with the recession in our transportation emissions. We've also seen a nice leveling off of some of our electrical emissions. That's been primarily a combination of conservation and switching from a coal to more natural gas, which is a lower CO2 per kilowatt. But we're still a big part of the problem. China passed us a few years ago in total emissions, but we're still way up there. There's a lot more that we can do. I'm sorry to say, Ove, that Australia actually passed us very recently in the per capita emissions. So we're no longer the best or the worst, whatever the case may be, but still there's much more that we can do. But we also need to encourage other countries to, we need to set an example, I think, in reducing our CO2 emissions. So let me just close up. Again, I had to put a few pictures of pretty things on here. Coming back to the oceans and say that I'm not suggesting at all that we're going to kill everything in the oceans, okay? Don't read too much into what I'm saying. We have real concerns over how the ecosystems will change. There'll be winners and there'll be losers. But think about our oceans today. There's an amazingly diverse array of organisms, from the smallest bacteria up to the largest predators, you know, even things like polar bears that are an active part of our marine ecosystems and are potentially endangered from the activities that we're making. I'm not saying at all that we're going to kill everything in the earth, but we are going to change our marine ecosystems. They are changing already. You'll hear some of that this afternoon. The real question is, are we as a society willing to accept the changes that we're forcing upon the ocean and upon our marine ecosystems? So I'll just leave it there. And again, the speakers yesterday all had a cartoon, so I had to put in a cartoon here. Thank you very much.
Thank you, Dr. Sabine, for that very informative talk. And thanks, too, for putting in that last section, pointing us in the direction where we can help. Now we all need to do our part. At this time, I'd like to invite our panelists back up front for the discussion, the question and answer period. And I'll remind folks that you can submit questions on pieces of paper being passed out by the ushers, or using the internet on Google Moderator, or by sending by email, or even Twitter. And we'll begin our question and answer period shortly.
slide him in under here. All right, I think we're ready for the question and answer to start. All right, thank you, Chris, for such a great talk. That was really a lot of fun. He made chemistry fun, didn't he? Students up here? Let's start. I'm sure the panelists have some questions. Actually, I think they've already been asking them while we weren't listening. I can't make eye contact with all of you now. I'm going to have to do the Q&A from up here. So, Barbara.
I thought I'd ask a challenging one. When do you think we're going to reach a tipping point where we, as one of the leading nations of the problem, have to change now, or we're dooming the planet for the young people in the audience? And as the leader of one of the labs in this nation, who's in charge of that science, when is it that we say enough is enough?
That is a very challenging question. I think the scientists are trying to say now that enough is enough. We are already seeing impacts from our changing climate. Ove will be talking about that with the coral reefs. We see it with the shellfish industry. We see it everywhere we look. The question really becomes, when will the general public recognize it? And I think that's in part an issue of education, and we're making much more effort to try and educate the community about what we know, what we don't know. There is this sense, I believe, in the country that the changes we're seeing are still in debate, and they're really not. And I think as soon as we can recognize that and help the country to recognize that there will be a rally of people going to Washington and saying, we need to do something about this.
All right, great answer. And to the youngsters in the audience, we need some rallies. We need everyone in this room to rally and make change now.
Occupy the oceans.
Yeah, occupy the oceans.
We already are. We are, yeah. That's part of the problem.
Not particularly good.
I have a question, too. I was surprised at that you could, that such a rapid response because of the economics, that you could measure. That's a measured difference?
Yes, that's a measured change.
Yeah. And is that a number of measurements scattered around the world, or is it?
Yes, I didn't have a chance to show that, but the CO2 emissions actually come from every country has to report its fossil fuel use, and we know the conversion from the barrels of oil burned to how much CO2 that releases. And so we can add all that up basically and get at the CO2 emissions.
So that's pretty impressive. I mean, it does show that that there's a cause and effect, that if we make a small change. I mean, I don't think most people realize that there was such a reduction in emissions, but there it is in the records. That's pretty good, I think.
That's right, yeah. So it's hard to argue that humans can't be making a difference in the atmosphere, and in these concentrations that we see, when we can see this direct cause and effect. We decrease our fossil fuel burning, and we see the CO2 drop.
Just one more quick one. How do we get around this issue? As scientists, we always say we need to know more, because we always want to get at the truth. We want the whole story. But I think the public, especially when there are jobs at stake, when you say we need to change now, but we need to know more, that you weigh the two things. And I think the prudent answer to most people, in most people's minds, well, let's wait and see.
Right.
And at one hand, we're sounding sort of an alarm saying we can't afford to wait much longer. On the other hand, we're saying that we really don't know all the answers yet. So, I mean, that's a tough one, right? Is it?
It is, but it's decisions that we've made in the past. Think about the ozone hole and the production of chlorofluorocarbons, these man-made compounds that are used for refrigerants and refrigerators and air conditioners. There was new science that came out that suggested that perhaps these man-made compounds were eroding the the ozone layer around the Earth. That would have dire consequences for humanity. An international agreement was made at the time when the science was even less well developed than it is now for climate change. There was a global agreement, and there were people saying then, this is going to devastate the economy. We'll have no more refrigerators or air conditioners in the world, and our society will collapse at the time. But there was an international agreement to do it, and we did it. And in fact, there were no dire consequences. The companies immediately found alternatives to those, and CO2 or CFCs are actually going down in the atmosphere. We can see that and document it. There's no reason why we can't do that with CO2.
And there would be... And there are some kinds of information that we maybe don't need right now. For example, if your house is on fire, you're going to fight the fire, particularly if you know that there are a lot of people in there, like maybe 7 billion. And then maybe later on you could figure out if it was caused by lightning or arson.
Mm-hmm. Right. And that's a really good analogy. Yeah. That is. That is correct. And it is unequivocal that the planet is warming. Mm-hmm. And it is unequivocal that the CO2 increase in the atmosphere is changing the chemistry and the fundamental marine ecosystems of our oceans.
I'll offer another analogy. It's a little bit like saying, should you love and take care of your child now, or should you wait until they grow up to see what kind of person they're going to turn into?
Okay, yeah, that's a good one too. Yeah.
Okay. Let me follow on to David's question that we started this thread on. From the audience, someone asked if we know what the cause of that spike upward after the trend downward in 2009. So the 2009 was obviously a set of economically driven choices. That spike upward in 2010 was probably choice-driven as well. Do we know anything about what lies behind that?
Yeah, so the big increase we saw in 2010 was primarily associated with, was not directly from the United States, although we saw in the United States emissions that there was a little bit of a spike there. So you may have heard in the news, there's been a lot in the news lately about our decrease in CO2 emissions. From 2010-11, it looks like it might be coming back up, so we can't get too comfortable. But the majority of that increase in 2010 was outside the United States, and particularly in Asia. China, in particular, has had a phenomenal growth in their economy, and they're bringing on new coal-fired power plants on a regular basis. And so I think what you see in that increase with 2010 is other CO2 sources from other countries, and that's why this truly is a global problem.
So I'd like to ask a question. Right at the end there, you showed the food webs changing and all that, and then you took pains to say, well, you know, I'm not saying that the oceans will be dead and so on. With shifting baselines, won't we just get used to it? And so we'll get used to eating jellyfish instead of tuna. We'll get used to having holidays where we won't see reefs, we'll see slimy algae, which we'll take photos and Google over. So, I mean, this is a problem. Maybe this is for Dr. Moore as well. You know, won't we just get used to it? Is there any problem with that? And eventually, Dave said that we could all fit into 1 kilometre cube if we didn't take up more than an airline seat. Exactly right. So we have the appropriate audio visuals and all of that, then we'll get used to that, won't we? I mean, what's the problem?
Yeah. Well, that was the question I was going to address to you too. You know, you say there's going to be losers and there are going to be winners. Are we the losers?
Well, it becomes a value judgment, right? So it's, I mean, the science is there. We are definitely seeing changes in our marine ecosystems. As I tried to say in my conclusions, the real question is not, are we changing, or it's are we as a society willing to accept those changes? Are we willing to eat jellyfish instead of tuna?
They're great to eat.
And that's...
I'm going to kind of jump in as a panelist a little bit. I study the deep rock record, the long ago times. And from what we can tell from high resolution climate proxy data, the last time CO2 levels changed as fast as this was 250 million years ago, and 92% of the species on the planet went extinct.
Yep.
You say that like it's a bad thing.
It's a cure.
Yeah, there have actually been 5 major sort of proxies for ocean acidification events in the past. Periods when there have been significant changes in ocean pH. And yes, unfortunately, all of those 5 have seen significant extinctions. But the oceans always recovered. It took them 100 million years to recover, but they did always recover. And we might be facing another one of those. The problem is, that's where I get into the importance of the rate of change, because in each one of those previous events, none of them are actually perfect analogs for what we're doing now. That while CO2 may have increased rapidly in the past, we can't really say that it's increased as rapidly as it is now, particularly if we get into this 150 or 400 times what we've seen in the past. That we don't really know what's going to happen then.
Isn't there also a significant risk in that, we really have no idea? Like you said, Wally Broker always shows this picture of us prodding an angry bull with a pitchfork. We know what's happening is bad, but we really don't know very well what the consequences are, and we don't know that they're necessarily adaptable. I mean, as the water cycle changes and you get large areas where you can't grow food, and can you still feed 7 billion people? So there's no certainty we can adapt to it.
Right, and there are, I think the point there is, there are indications in the geological past of other semi-stable states of our climate system. Just think about the ice ages, right? We know that a 100 part per million drop in CO2 concentrations from 280 parts per million to 180 parts per million was enough to drive us into an ice age where we would have 2 miles of ice on top of us right now. We've already increased the CO2 from that 280 by 100 parts per million, the equivalent amount of what drove us into an ice age with the drop in CO2. How might we be poking the climate monster and saying, I dare you to try and find a new stable state for the climate? We just don't know.
I have a question.
Oh, go ahead, Bill.
With respect to the terrestrial biosphere, that's a relatively short-term sink, and there'll be a return. It won't continue to take up as much CO2 as it is currently, and so that could exacerbate the issue with respect to absorption of CO2 by the oceans, and also the increase in the atmosphere.
Right, and that's a subtlety that I didn't really have much time to get into. Ultimately, the long-term sink for all the CO2 that we're releasing will be in the oceans. The terrestrial biosphere right now is absorbing quite a lot of carbon dioxide, as much as the oceans, it looks like. But in the past, it actually was a source. And a lot of the reason why it's absorbing CO2 now is because we're regrowing the forests that were cut down. Think about the early 1800s as humans were spreading across the planet, chopping down forests. Our primary mode of survival was agriculture, so we cut down all these forests. There was a huge pulse of carbon dioxide released to the atmosphere at that time from cutting down all those trees. What we're doing now is just reabsorbing that CO2 as those trees grow back, but it's not sustainable. There is a lot of argument about whether the CO2 fertilization, the fact that trees grow faster in high CO2, how sustainable that is, whether that will continue, because typically what we find in natural systems is that once one thing stops becoming limiting, something else will become limiting. And some of these forests that started to grow really quickly under elevated CO2 actually have slowed down now because they become nitrogen limited. And so there's a lot of question about how that will happen. But in the long term, you saw that where most of the natural carbon is found in the ocean, so the oceans ultimately will absorb that carbon dioxide. The problem is it's a long process. The turnover time for the whole ocean is on the order of 1,000 to 1,500 years. When we're making these sort of changes on time scales of decades to centuries, there's only so much the oceans can do.
Let me interject one from the audience here. Someone asked a sort of follow-on to this, when will the oceans stop absorbing? And then will it all just accumulate in the atmosphere? So is there going to be a change in that ratio over time?
Right, so the ocean, think of the ocean as kind of a two-layer system. We saw yesterday a couple of times this conveyor belt idea that you've got surface waters that in a few specific places are pulled down into the deep ocean and then kind of mix around in the deep ocean. And there really are these layers. What we're seeing, I showed you that in the surface ocean, CO2 is increasing at about the same rate as the atmosphere. And we see that pretty much everywhere. And there really is no realistic theoretical limit to that. You know, think about your soda. As you open a can of pop, there's a tremendous amount of CO2 that's been pumped into that. And when you release that pressure, the CO2 comes out. But there's an amazing amount of carbon dioxide in that soda. Basically, we're turning our oceans into sodas, right? We're adding that CO2. But the limiting step is how quickly, because there are only a couple of places where the water moves down into the deep ocean, it's limited in how quickly we can move that carbon dioxide into the deep ocean. And that's the part that takes thousands or 1,500 years to do. So while the surface ocean will continue to increase at the same rate as the atmosphere, if we add CO2 faster and faster, and we're actually seeing this already, it won't be able to absorb enough. There's not enough volume in that surface layer of the ocean to take up all the CO2 from the atmosphere, and we'll see an acceleration of the rate of change.
Okay, so Ove and then Carl.
Just following on the heels of that, is it possible, given it's getting more acidic, that we could add a base to the ocean and manipulate the pH back up?
So that's where I like to start my talk with this coal train analogy. To think about the mass of base that you would have to add to counteract that. I mean,
it's a new industry.
It's just inconceivable. In theory, yes, but in practice, no. I mean, there have been ideas that we can take. There's a lot of fossil calcium carbonate around in the world. The White Cliffs of Dover, calcium carbonate. We could take them, grind them all up, and dissolve them into the ocean. The problem is that there's about a 4-to-1 ratio. You need 4 times as much calcium carbonate to fix an amount of carbon. So the mass of calcium carbonate it would take to neutralize, ultimately that's what the oceans will do. But they're going to do it on time scales of millions of years, and it's just not practical to try and do that short term.
You showed that the average U.S. vehicle gets 17 miles per gallon. I was very surprised it was that bad, and I thought it was around 20. And that's obviously a matter of individual decision, because in China they get a much better mile per gallon rate, right? So I'd like to know, among other things, since you know a lot about all of this, what do you do in your personal life to reduce your carbon footprint? And what do you think is the wise balance between what individuals can choose to do, like have very low mileage vehicles and choose to spend a lot of money on gasolines, and how much the government should impose efficiency?
I should say that's a really common question from our online and our audience here too. That was next on my list. So
there you go.
Okay,
now you have to answer.
There you go. Now I'm on the hot seat. You're right. I mean, it ultimately comes down to personal choices. You know, I chose to, and it's, I should say the choices are not always obvious. And may not be what you think. So I chose to buy a new vehicle, to buy a hybrid car, so that I can get that higher gas mileage. But that doesn't mean that you're necessarily doing the right thing. If you've got a car that's 1 to 2 years old, I was driving a 12-year-old Nissan at the time that I chose to do that. You know, it's not just CO2. If we all go out and buy all new cars today, there'll be a huge pile of dead cars that we have to deal with. Everything has consequences, right? There was a study done in Costa Rica, I think. They decided to really push switching to biofuels and decreasing their dependence on foreign oil. I'm sorry, no, it was in Brazil, and so they obviously have gotten a bad rap for all the deforestation. So they've been really pushing biofuels, and with the idea that would decrease their CO2 footprint. In fact, they found that it went up because the rate of deforestation increased because they're cutting down the rainforest to grow the crops for the biofuels. So there are sometimes unintended consequences. But I think there are things, you know, I've changed all my lights to compact fluorescence. We turn all our power off whenever we can. There are little things you can do, carpooling, that can reduce your personal CO2 footprint that I try and do, while at the same time promoting conservation and voting according to environmental policies rather than just
Okay, so, but the second half of my question is, what do you think is the wise role of government in setting standards? Because you do that, but a lot of people do other things. A lot of people have 17-mile-per-gallon cars.
Right, and that's a tough one because there are so many different priorities and competing attention in the political realm that I think it would be great if the federal government could step up to the plate and impose regulations that would move us towards a reduced reliance on fossil fuels. But the economy is important as well, and they have to do a balancing act to move us forward. That being said, I don't think we can pin all of this on the government and say, well, it's up to the government to make it happen. I think we all need to take personal responsibility and say, all right, if the government is not stepping up as much as we think, which is what the polls say, then what is it that I can do to make a difference in there?
Maya, you had a question?
So I had a question. You had in one of your slides a very optimistic little line in the corner from Scientific American where it said I think it was 480 billion, you could build solar arrays in the U.S. that would provide 60-something% of our...
69% of the U.S. electrical needs could be serviced by putting one array of $400 billion in the Mojave Desert.
Okay. And can you talk a little bit more about that? I mean, it just sounded so promising. And I mean, is it huge?
No, actually, I didn't show it, but there's a map. You can't even see the spot on the. I don't recall exactly the area, but it's fairly small. And you think about, you know, how much did we spend on the Iraq War versus what we could have spent to reduce our reliance on fossil fuels.
Do you see any sort of political will to do something like that? Is that possible?
Again, I think there is the will to do it, and people, the government and politicians see the advantage of moving in that direction, but it becomes an issue of what is politically possible, and it's a balancing act.
Barbara, you had a question?
So Chris has done an eloquent job of pointing out today that Earth is at a tipping point, and we as scientists have been aware of this for some time. We know that we're not effectively getting the message out, so to Chris and to the audience, the question is, what more can we do if we as scientists can bring these facts to all of you, and yet we lack the skill or the translation to the public and to the press? So, Chris, what do you think?
You know, that's why I like the oyster story. The nice thing with the oyster story is we're a government agency that started working with our commercial partners. They had a problem. We came in and helped them to address that problem. The oyster industry in the Pacific Northwest is sold. They are our biggest advocates right now in terms of promoting continued studies of ocean acidification. They have very strong lobbies in Washington, D.C., and they are now basically making our case for us. They also are going out and talking to the national shellfish industry, saying, hey, here's what we found in our situation, and we're seeing similar effects. We've shown now with preliminary results in the Chesapeake and in the Gulf of Maine that both of those shellfish industries are also being impacted by ocean acidification. Now, the drivers for that are a little bit different. They don't have the upwelling. It's more eutrophication, but they're seeing that same effect too. I think the real power in this country comes with industry. So if we can start working with our industry partners and show them the benefits of moving to a greener society, of moving away from our reliance on fossil fuels, that they will become our advocates and we'll start to get that word out. But that's very new and unusual and different for scientists. You know, we tend to do our own little research and publish in our scientific journals and not talk to anybody. And one thing that we've been doing, particularly in NOAA, is as a mission agency, we have that responsibility to interact with the commercial shellfish and fisheries industries and to work with those partners. And I would hope that some of my academic colleagues would do the same thing and partner more with industry. And you know, we tend to look down on practical applications of our science, but I think in this case it really can provide a benefit to everyone.
And Chris, we have several questions here from the audience and the online audience, asking whether a lot of the things you talked about today are applicable to, say, fisheries in the Great Lakes and those kinds of things. Do we have the same kind of chemistry going on in our large lakes, maybe even in our small ones, as in the ocean?
Yes, so that's an excellent question. The basic chemistry and thermodynamics of the ocean acidification still holds true in freshwater. Anytime you increase the concentration of a gas over a body of liquid, that gas will move into that liquid as long as the concentration is higher. And so we are seeing ocean acidification in the Great Lakes and in the freshwater systems as well. What is less well studied and understood is how that will affect the local ecosystems. Freshwaters are a little bit different in the oceans in that they tend to be less buffered. And so, as I mentioned, the oceans have a lot of chemicals in them, basically, to keep it in simple terms. And those chemicals prevent the pH from changing too drastically and too quickly in the oceans, because there are all these other chemicals that can absorb and release hydrogen ions as needed. In freshwater, you don't have that so much. So the pH extremes changes are much larger, and the ecosystems in those freshwater lakes tend to be more adapted to those situations. Now, whether we're going to affect them because we are changing the baseline pH of those systems is still yet to be seen. But there is a thought that perhaps they're a bit more resilient, but more research is needed. Something for all you guys to do.
I was going to say, that sounds like a Gustavus research project. If you, and this may be a question for the whole panel, but if you could suggest one book that a high school student ought to read about this topic, what would it be? I'm sure they can read more than one.
Well, what do you guys think?
I would read
Carl's got some books.
Carl's written some books.
My most recent book, which is called The View from Lazy Point, A Natural Year in an Unnatural World, goes into this a lot, and the implications, scientific, economic, and ethical. So since I've created the opportunity for me to give that advertisement.
I get a kickback, right?
Yes, you do. Yeah. As soon as I get rich, you get all the profits.
Okay.
So there are a number of very popular books that try and explain what's going on with climate change, where the state of the science is, the political and economic ramifications. And I certainly recommend that you read some of those. But as a scientist, for me, it ultimately comes down to what is the core science. And so while it may not be the most interesting reading, I think the most important document that I would recommend would be the Technical or Summary for Policymakers of the IPCC. That is a consensus document put together by thousands and thousands of climate scientists that have painstakingly gone through all of the relevant scientific literature and condensed it down into what may not be popular or exciting reading, but it's got the main points. And if you really want to get at what is the core science of what do we really know and what don't we know, that's the ultimate authority.
But Chris, may I say that your presentation was one of the best, most lucid ways that I've ever heard this presented. And I think sharing that with your colleagues and friends would be great too. I mean, I thought that was very well done.
Thank you.
And I think we'll end the Q&A with one more question.
I was going to help answer that one, because for the high school students, I think that you might consider a book that's called Strange as This Weather Has Been, which recounts the story of a family that is right there at the bottom of a mountain as the mountaintop is being removed for the extraction of coal. And it's very important to understand the science. It's also very important to understand what happens to people when their basis of their existence is torn away and burned. So I would recommend a little fiction to get into people's minds and hearts and to really understand not only the science, but the heartbreak.
And for those of you that don't read, there's a full-length movie called A Sea Change that I would highly recommend that you watch. And you can get it on Netflix, I think, and learn about ocean acidification there.
All right. Well, thank you, Chris, and thank you, our panelists. And we'll see you all after lunch.